Next, we are going to study the third Hubness-Aware classifier called naive Hubness-Bayesian nearest neighbors. If you are familiar with naive Bayesian classifiers, you will probably soon recognize that what happens is a naive Bayesian inference. However, in this naive Bayesian inference, instead of using the actual attributes of the instances, we use the nearest neighbors of the instances. So what happens is a naive Bayesian inference over the nearest neighbors of an instance. If you don't know what is a naive Bayesian classifier, don't worry. I hope you will be able to understand this classifier even without knowing what is a naive Bayesian classifier. Again, we use our running example to illustrate how this classifier works. Just as always, we want to classify the yellow triangle. First, we will estimate the so-called a priori probability of the two classes. In this example, there are 6 instances from the class of circles and there are 4 instances from the class of rectangles. That is, in total, we have 10 instances. Therefore, we can estimate the probability of the first class, that is, the probability of the class of circles, as 6 divided by 10, which gives 0.6. Similarly, we can estimate the probability of the second class as 4 divided by 10, which gives 0.4. This will be the probability of the class of rectangles. Just as always, we use 2 of the nearest neighbors of the triangle in order to classify this triangle. These 2 nearest neighbors are, of course, instance 6 and instance 9, just like before. For these 2 instances, we will calculate a so-called conditional probability. In particular, we will calculate the probability of instance 6 appearing as one of the nearest neighbors of instances belonging to the first class. And similarly, we will calculate another conditional probability, which is the probability of instance 6 appearing as one of the nearest neighbors of instances from the second class. As there are 6 circles in this example, and instance 6 never appears as neighbor of one of the circles, therefore the probability of instance 6 appearing as a neighbor of another instance belonging to the class of circles is estimated as 0 divided by 6, which gives 0. Similarly, the probability of x6 being the neighbor of a rectangle is estimated as 2 divided by 4 because in total there are 4 rectangles and x6 is the nearest neighbor of 2 of them. We calculate the same probabilities for x9, that is, for the second nearest neighbor of instance 11, and finally we assess the probability of both of the classes as it can be seen in the bottom of the slide. In particular, the probability of instance 11 belonging to the class of circles, that is, belonging to the first class, is proportional to 0.6 times 0 times 0.167. And this product obviously gives 0 because one of the terms of the product is 0. Similarly, the probability of instance 11 belonging to the class of rectangles is proportional to 0.05. As the probability of belonging to the rectangles is higher than the probability of belonging to the class of circles, this triangle will be classified as a rectangle. This example also illustrates that a simple maximum likelihood estimate of probabilities may be problematic in some cases, because such a maximum likelihood estimate may simply lead to zero estimates, and these zeros can turn the entire product into 0. Therefore, we may use some more advanced techniques to estimate the probabilities, such as a Laplacian estimate of the above conditional probabilities. In case of a Laplacian estimate, what we are doing technically is the following. While we are calculating the above fractions, we add the small number to the nominator and we add this small number times the number of classes to the denominator. Here we can see a more general description of the naive Hubness-Bayesian k-nearest neighbor classifier. While we are classifying a new instance, we want to assess the probability of this instance belonging to the different classes. And this probability is estimated as a product. Or, to be more accurate, we may write that the probability of an instance belonging to class C is proportional to a product which can be seen in the right of the formula. The first factor of the product is the a priori probability of class C. Subsequently, the conditional probabilities of the events that the nearest neighbors belong to the class C are multiplied together.